Let's do a little practice of projecting one vector onto another. We'll start geometrically or by the picture. We'll do a little bit of simple numerical calculation as well in this video. So we're going to project vector v onto vector u. Okay, so we have our notation here projecting onto the lower vector. And if you recall, what we've done for practice is you sort of imagine almost like a light source casting a shadow of one vector onto another vector's path, and we want that path to be, perpendicular to the vector you're projecting onto. And in this case, the projection would be the vector that goes from here to here. I don't have any labels on these points, so I'm just drawing a simple little visual. It should be pretty clear from this that what we've got cooking is some form of a scalar multiplied by vector u. It's in the same direction as u, which is a scalar, which is what the formula shows, but you know how it is when you memorize formulas or you have formulas you're looking at. They may just look like some sort of code or foreign language to us, to our eyes. So let's do a quick little verification of this. If we were to let vector v be the vector 1, 1, and vector u be the horizontal vector that goes 3 units to the right but does not go up or down, and I could use the ij notation, 1i plus 1j for the first vector and 3i for the second vector, but I like the component form for computation purposes as a teacher. So our projection of vector v onto vector u is what you get when you do the dot product of the two vectors divided by the magnitude of the vector you're projecting onto squared. As a recollection, I frequently use the single, almost like absolute value symbol for magnitude, because absolute value is a form of distance as well, if you recall. And then this is all multiplied by vector u. Make sure you remember that little dot there, that's a time symbol, because this is not a vector right here, it's just a scalar. All right, quick calculations. U dot v would be 1 times 3 plus 1 times 0. And, I didn't do this yet. I got to find the magnitude of that vector there. Well, that magnitude is going to be 3 units long. All right, so let's put that in here. 3 squared times the vector u. That's going to be 1/3 times vector u, which is 3, 0, which is equivalent to the vector 1, 0. All right, let's go back up here again. This vector here, that is horizontal. It's 1 unit long. I think if we had drawn this on graph paper, you would completely believe that it's 1 unit long. All right, there's a quick little calculation numerically. All right, let's go back and do another visual. What if we were to take the same two vectors, but project vector u onto vector v? So in this case, we have to take the path of vector v and extend it and imagine not horizontal, but a light source of sorts that is going to be orthogonal or perpendicular to vector v. Right angle here. Oh, that's a horrible right angle. And the projection of vector u onto vector v starts here, and it goes all the way till we get to that perpendicular point. Looks like vector v times some scalar a little bit bigger than 1 would be what we'd get here if we were to do that same calculation as before. We're not going to do the calculation on this one, but I think you should use the same two vectors I just used previously and give it a shot. One last calculation. Let's do projection of this horizontal vector W onto vector V. All right, we'll extend V in this direction. Imagine that orthogonal. Not very nice looking there. Starting here and going this way, that would be our projection of W onto V. We'll do a quick little numerical calculation, I think, for this one. Practice. Let's let W be the vector that goes left 1 but does not go up or down, -1, 0, or -I. And let's let vector V be the vector that is 3 units to the right and 2 units up. Then the projection of W onto V would be equal to the dot product of the two vectors, which would be -1 times 3 plus 0 times 2 over some magnitude squared, which I have to calculate, and then we'll multiply by vector V afterwards. So what is the magnitude of vector V? What is its magnitude? I think we will find that's the square root of 3 squared plus 2 squared root 13. That's right. So that would be square root of 13 quantity squared. Let me slide up and give us a little bit more room. That vector, that projection we're looking at there, would be equal to -3 thirteenths multiplied by vector V, 3, 2, and if we distribute, we would get -9 thirteenths, -6 thirteenths. Now, we do a quick little picture check on this one. Please note that this projection that we just drew happens to be in the opposite direction of vector V, and that angle theta happens to be more than 90 degrees, or obtuse. When we did the dot product calculation, we got a negative number, which just verifies some things we were working with the cosine of theta formula, which also involves the dot product. Cool, huh? All right, that's it for now.